There is a joke that has been passed around in energy economic circles for almost 6 decades. It is short, cynical, and devastatingly accurate. Nuclear fusion, they say, is the energy of the future, and it always will be. I first heard that line from a retired energy policy advisor who had spent 30 years watching government funding cycles come and go, each one promising a clean energy breakthrough that never quite materialized. He laughed when he said it, but there was a real tiredness behind the laugh. Because the frustration embedded in that joke is completely earned. Generation after generation of brilliant physicists poured their careers into trying to tame the energy of the stars here on Earth. And generation after generation of economists watched those careers end quietly without a commercially viable reactor to show for the effort. To understand why this joke survived for so long, you have to understand what fusion actually demands of an engineer. It is not simply a matter of building a bigger furnace. To generate energy through nuclear fusion, you have to recreate the conditions that exist inside the core of a living star. You have to heat hydrogen isotopes to temperatures exceeding 100 million degrees Celsius. The actual center of our sun sits at roughly 15 million degrees. So you are not trying to match the sun. You are trying to build something significantly hotter than the sun right here on the surface of Earth. Then, once you have this superheated mass of charged particles raging at temperatures no solid material can physically touch, you have to trap it in a precisely shaped magnetic cage, keep it perfectly stable, and harvest the enormous energy it releases as heat. And you have to do all of that while spending less electricity on the magnets and the heating systems than the fusion reaction itself produces. That last part, achieving what physicists call net energy gain, is where every single machine on Earth failed for 50 years. I spent a long time thinking that joke would never die. Then I started tracking the infrastructure spending data coming out of Anhui province in eastern China, and something in that data changed my mind completely. It started as a routine cross-reference exercise. I was looking at heavy equipment logistics, specifically the shipping routes for ultra-large industrial cranes and specialized cryogenic equipment moving through the rail corridors feeding into Hefei. The volume and weight class of the cargo did not match any announced industrial project in the region. I pulled the construction permit registries for the Hefei Comprehensive National Science Center and started cross-referencing them with satellite imagery. The footprint of what was being built on the eastern edge of the campus was expanding at a rate I had not seen outside of semiconductor megafactory construction. Hundreds of structural engineers were rotating in shifts around the clock. Heavy concrete foundation pads were being poured in a continuous cycle. Massive steel reinforcement columns were going in at a scale appropriate for heavy industry, not a university research annex. But the blueprints that eventually surfaced through international scientific registry filings told a completely different story. What was being assembled inside those concrete walls was the most ambitious fusion energy machine ever designed specifically for the purpose of connecting to a commercial power grid. Its official designation is the Burning Plasma Experimental Superconducting Tokamak. The scientific community knows it simply as BEST. And when I analyze what this machine is actually engineered to do, the old joke about fusion energy stopped being funny. It stopped being a comfortable, distant abstraction. It became a very immediate and very real geopolitical reckoning. To appreciate what makes this machine different from everything before it, I need to take you back to the specific wall that blocked every fusion program on Earth for half a century. Physicists call it the green wall density limit. Inside the type of fusion reactor used by most major programs, a design called a tokamak, you have a large donut-shaped vacuum chamber wrapped in powerful superconducting magnets. You inject a gas mixture of deuterium and tritium into this chamber, then blast it with enormous electric currents and radio waves until the heat strips electrons away from the atomic nuclei entirely, turning the gas into a glowing, superheated fluid of loose charged particles called plasma. For fusion reactions to occur at a meaningful rate, you need to compress this plasma to a very high density. Pack more nuclei into a given volume, and the chances of two nuclei colliding with enough force to fuse and release energy go up significantly. But the moment scientists tried to push past a specific density threshold, the plasma became violently unstable. Tiny tears formed along the edges of the plasma column. Heat bled outward toward the reactor walls at a catastrophic rate. The entire carefully managed plasma configuration collapsed in a fraction of a second. This density ceiling meant that every reactor on Earth was operating in a regime where achieving a true burning plasma was simply impossible. They were all stuck consuming more external power than the fusion reaction produced, trapped in the same mathematical dead end for 50 years. Then, a research team working on a predecessor machine in Hefei, called the Experimental Advanced Superconducting Tokamak, did something that sent a genuine shock through the global plasma physics community. They broke through the ceiling. Not by brute force, but by being fundamentally smarter about managing the plasma's internal behavior. The specific mechanism they developed is a real-time, algorithm-driven magnetic field control system. During a plasma pulse, thousands of tiny instabilities arise every second. In every reactor before this, these instabilities would build on each other, cascade, and eventually tear the plasma apart. The Hefei team engineered a control loop that could detect the earliest signatures of these micro-instabilities and apply precisely calculated magnetic field adjustments to suppress them before they could grow. They also redesigned the internal wall lining using a material that reduces the heavy impurities contaminating the plasma core. The result was a plasma pulse lasting over 1,000 seconds. More than 16 continuous minutes of stable, high-performance plasma operating well above the theoretical density limit. In the context of fusion physics, that is not a modest improvement. That is a fundamental rewriting of what is physically achievable inside a magnetic confinement device. They had found the tuning pattern that keeps an artificial star from self-destructing inside its magnetic bottle. And that discovery is the entire scientific foundation on which every component of the new BEST facility is being designed and assembled. The physical scale of what they are putting together in Hefei is genuinely staggering. The most recent construction phase involved the installation of the single most critical structural component in the machine, the Dewar base. This base structure alone weighs hundreds of tons and is precision machined to tolerances measured in fractions of a millimeter. It will eventually support a total equipment load exceeding 6,000 metric tons. To give that number a real sense of scale, that is heavier than most modern naval surface combat vessels, all concentrated onto a single reinforced foundation pad.